Alright, welcome back everybody. In this video we're going to look at how we're now going to find the exact area under a curve using RRAM. We've approximated the area under the curve using our different RAM methods, and we've looked at how we can take summations of things, and we're going to now combine those two things to enable us to find the exact area under the curve using RRAM. So the first thing we're going to do in order to do this is we're going to set up an RRAM formula for some general number n of rectangles. And then we're going to manipulate that formula to turn it into summations, where we've got the sums that we can now convert using our helpful sum rules. And after we're done doing all that conversion, what we're going to do is we're going to take the limit of this formula as n goes to infinity, and by doing that, by letting the number of rectangles approach infinity, we're going to get the exact area under the curve. I know we talked when we were first using the RAM methods, we talked about how we wanted to use more and more rectangles for greater precision. Well, we can't use any more rectangles than an infinite number of them, and so this is going to give us our actual exact value. So let's look at the first example here. We're going to find the exact area under the curve y equals x squared plus 3 from x equals 0 to x equals 4. And I'm going to tell you that my graph here will not be to scale. But we're going to find the area under this curve. Okay, now I need to figure out the RRAM formula that we're going to use to represent the area under this curve. And so let's see how I'm going to do that. Well, first of all, in order to find RRAM, I need the width of each of the rectangles. And we talked before that the width of each rectangle was just the width of the interval divided by the number of rectangles. And so the width of each rectangle here is going to be 4 divided by n, because our interval is 4 units wide and we're subdividing it into n rectangles. So suppose I again, not to scale here, I start putting these n rectangles in. The question now becomes what I'm going to use for the heights of those rectangles. And the first rectangle's height, since we're using RRAM, is going to be the value of the function right here. And the second rectangle's height is going to be the value of the function right here. And the third is going to be right here. And the question really becomes, where are those values? Well, since each rectangle is 4 over n units wide, we're finding the height here at 4 over n, because this rectangle is 4 over n units wide, and it starts at 0, and so the x value at this right endpoint for this rectangle is going to be 4 over n. So we're going to put 4 over n into the function, and that gives us the value of the height of the first rectangle. Now, where's the second rectangle? Well, again, this width is 4 over n, and so we're going to find the value of the height of the function at 8 over n. So we'll put 8 over n into our function. And then the next rectangle, that happens at 12 over n. And so we'll do that. And we'll keep doing that for rectangles. We'll do all of that all the way up until the point where we get to the last rectangle, and the value of the function at the last rectangle is just substitute the right endpoint, 4, in there. I'm going to do that, but I'm going to write 4 in a slightly different way so that I maintain uniformity with all of the other things that I've written thus far. I'm going to write this as 4n over n because that simplifies to 4, but it maintains the same form that we've got in all of these, where we've got something divided by n. Okay, so there is our RRAM formula that represents the area underneath this curve. Now, I'm going to convert this into a summation. The 4 over n stays in front. Now I want to write the sum from k equals 1 to n of some expression. And we have to ask ourselves what that expression is. Well, when k is 1, it's going to represent this first expression when k is 1. When k is 2, it's going to represent this expression. When k is 3, it's going to represent this expression. And hopefully you can see that this means that all we're doing is taking 4 times the k value over n and squaring it and adding 3 to that. Okay, so far so good. Now what we're going to do is we're going to manipulate this expression algebraically so that we get only summations multiplied by other things. So we've got 4 over n times the sum from 1 to n of 16k squared over n squared plus 3, which is equal to 4 over n, I'll use my sum rule here, times the sum from 1 to n of 16k squared over n squared plus the sum from 1 to n of 3. And now with regards to this summation, what's variable within the summation is the value of k. And so everything that doesn't contain a k in here is constant with regards to this summation. So I can further simplify this to 4 over n times 16 over n squared times the sum from 1 to n of k squared plus the sum from 1 to n of 3. Okay, can I remember that when I turn the page? No, so I'm going to jot it down real quick off to the side here so that I can bring it back when we get over to the next page in order to simplify this more. Okay, now that we have that, we're going to bring it over here. And what we had was 4 over n times 16 over n squared times the sum from 1 to n of k squared plus the sum from 1 to n of 3. Now I'll use my helpful sum rules. I've got 4 over n times the quantity 16 over n squared times n plus 1 times 2n plus 1 all over 6 plus 3n. And I'm going to distribute the 4 over n through this. I'll distribute it first to these terms. And when I do this, I'm going to do what I've always referred to as a little denominator switcheroo. I'm going to group all the numbers together, which is going to give me 64 over 6. I'm going to group all the numbers in one fraction and all the n's in another. And then I need to distribute the 4 over n into this second term as well. 4 over n times plus 3n gives me plus 12. Alright. And now what I need to do is I need to take the limit as n goes to infinity of this expression in order to find the exact area underneath the curve. And because of limit rules that we already know, this is actually going to be equal to, I'm going to reduce the 64 over 6 to 32 over 3. This is going to be 32 over 3 times the limit as n approaches infinity of n times n plus 1 times 2n plus 1 all over n to the third. And that's what's inside the limit. And now I just need to figure out the value of the limit as n approaches infinity of n times the quantity n plus 1 times the quantity 2n plus 1 all over n to the third. If you remember how limits as n approach infinity of rational functions work, we only need to consider the highest power of n in both the numerator and denominator. The highest power of n is what we get by multiplying those three things together. So really this is like the limit as n goes to infinity of 2n cubed over n cubed. The n cubes cancel, and that limit value is just going to be 2. And then I can add these two things together, 64 thirds plus 12, and we end up with 100 over 3. For the exact area underneath the curve, y equals x squared plus 3, from x equals 0 to x equals 4. Alright, that's where we're going to end this video, and we'll come back in the next one and go ahead and work our way through example 2 in the same fashion with a little bit less detail. See you guys next time. Have a great rest of your day.